For an infinite interval, we define the integral from a to infinity of f of x dx as the limit as t approaches infinity of the integral from a to t of f of x dx. This turns an improper integral into something we can actually work with by first treating it as an ordinary integral up to a finite point t. We say the improper integral converges if that limit comes out to a finite number, and we say it diverges if the limit is infinite or does not exist at all. So the whole question of convergence just becomes a question about an ordinary limit. The same idea applies when the integrand itself is discontinuous at the upper limit b instead of the interval being infinite. There you replace b with a variable approaching b from the appropriate side, and again take a limit of an ordinary definite integral. There is also a comparison test that lets you decide convergence or divergence without ever computing an exact value. If f of x is between 0 and g of x, for all x greater than or equal to a, then, if the integral of g converges, the integral of f must also converge, and if the integral of f diverges, the integral of g must also diverge. Now let's work through an example. We want to determine whether the integral from 1 to infinity of 1 divided by x squared dx converges. Following the rule, the very first step is to rewrite this as the limit, as t approaches infinity, of the integral from 1 to t of x to the minus 2 dx. Notice we have not touched infinity directly. We've turned it into a limit of an ordinary definite integral. Next, we find the antiderivative of x to the minus 2, which is minus 1 divided by x. Now we evaluate this antiderivative from 1 to t. That gives us minus 1 divided by t minus the quantity, minus 1 divided by 1. Simplifying, that's 1 minus 1 divided by t. Finally, we take the limit as t approaches infinity. As t goes to infinity, 1 divided by t goes to 0. So we're left with 1 minus 0, which equals 1. Since this limit is a finite number, the integral converges, and it converges to exactly 1. Here's a useful trick for integrals of the form, the integral from 1 to infinity of 1 divided by x to the power p dx. You don't need to redo this whole computation every time. Just look at the value of p. The integral converges if p is greater than 1, and it diverges if p is less than or equal to 1. Our example had p equals 2, which is greater than 1, so it had to converge, matching what we found. Now, the most common trip-up, do not treat an improper integral like an ordinary one, and just plug infinity straight into the antiderivative. That shortcut can silently hide cases where the limit doesn't actually exist, and it skips the reasoning that tells you whether you're allowed to call the integral convergent at all. So here's the teaching tip to remember. Never write the infinity symbol directly inside an integral's bound without first rewriting the whole expression as a limit of a definite integral on its own separate line. Treat that rewrite as a mandatory first step every single time, not an optional formality you can skip.